to ask follow-up questions later on. So next up is Dr. Bashir Kazimi. He leads a research group at the Institute of Materials and Materials Data Science and Informatics at the Forschungszentrum in Jülich. He works on self-supervised and foundation models for scientific imaging and is a recipient of the Young Excellent Scientist Program Award at Forschungszentrum Jülich. And today he will talk about what happens when data augmentations respect measurement physics and show that this can substantially improve learned representations. We're looking forward to your talk.
Thank you very much. Good morning, everyone. So today I'm going to talk about how we can learn better representations when we design augmentations that are physically valid. And we apply this to electron microscopy images. The motivation for why we need AI for electron microscopy is that we have lots of high-dimensional data because modern microscopes generate terabytes of complex data at a very fast pace. They are noisy and incomplete signals, and missing information is very common in electron microscopy. And to scale the manual analysis is not possible because it's very subjective and time-consuming. These images show the range of complexities in electron microscopy images that we can have, from in situ transmission electron microscopy of nanocrystalline grains to nanoparticles to diffraction images of phase change materials. So this is where AI and deep learning can help us automate the analysis in order to accelerate scientific discovery. So as we all know, the standard workflow in deep learning is if you have a large data set, you train your model end-to-end, and you get a decent score, a decent performance. But if you have a small data set, similar to what our previous speaker, Simon, talked about, you pre-train your model on a large data set from another domain, and then you fine-tune this on your own domain. But the problem is that we have very few labeled data sets in electron microscopy and also in other scientific imaging domains. And if you want to annotate them, you really need some domain expertise. And to scale annotation is very time-consuming and expensive. And the solution is we need models that learn from unlabeled data, and this is where self-supervised learning comes into play. And in self-supervised learning, similar to what Simon talked about in the previous presentation, you have two different augmented views of the same image that you're trying to train the model to learn to bring them closer. But if you have augmented views of different images, you want them to be pulled apart. And these augmentations, these changes, perturbations that you do to the images are the invariances that the model learns to ignore. For example, if you have the original image, you crop it, you flip it, you change the colors. The model ignores those variations because it's still part of the same image, so it is forced to learn to produce representations, so similar vectors for all of those random augmentations. And that's for natural images. But scientific images, such as electron microscopy, they are measurements and they are not photos. So those standard augmentations won't work well. In electron microscopy and diffraction, some of these transformations that you apply on natural images and they work well, they will basically destroy the physics behind those images in scientific domain. For example, if you have a cat image, you horizontally flip it, it will still be a cat. And these invariances in natural image domain are not only harmless, but they even help the model to learn better representations. But in diffraction pattern images, if you flip it, you basically change the crystal orientation, and that's not what is desired. You want the model to be able to differentiate between a diffraction pattern and the flipped version of it, and knows that they have different crystal orientation. So our idea is to build or design augmentations from the measurement physics directly. So that means we design augmentations that are symmetrically consistent, for example, rotations, but we drop those that destroy the physics behind scientific images. And also, we take into account the acquisition variability, for example, perturbations that are produced during image acquisition. We simulate this and encode this into our model. We do experiments, pre-training on 2 different electron microscopy modalities. The first one is the real space electron microscopy. This is a large data set of cellular electron microscopy data set. They come from different microscopes, transmission electron microscopes, scanning electron microscopes, and they contain images of different biological samples. So it's very diverse. We also pre-train model on another data set, simulated data for the stem in the reciprocal space, and this is from lithium nickel oxide, or LNO. And this data set is simulated, so it's very physically consistent, so you can validate your approach better. For these 2 data sets, we pre-trained 5 different SSL families, and we tried to cover as many different families of SSL architectures as possible. Simon talked about some of them in the previous presentation. So Dino V2 is the student-teacher based architecture. We also use the contrastive learning, Sinclair, masked image modeling, the masked autoencoder model, VICREG, which is based on redundancy reduction, and finally the image JPA, which is joint embedding predictive architecture. So the 5 different SSL families, they use the same backbone, they use the same hyperparameters. What we change is only the augmentations. So we have these different sets of augmentations that we do experiments with. First of all, we do pre-training with different SSL families using the original augmentations that come with those architectures that are applied to natural image domains, so we call it T-orig. And then we do the physics-aligned augmentations pre-training, so for electron microscopy, real space electron microscopy, and for the stem, so reciprocal space. So we show which augmentations we remove and which augmentations we add that encode the physics behind those operations. For downstream tasks, we also have 2 different electron microscopy modality. We have the NFFA Europe 100% SEM data. This is SEM images of diverse samples, 10 different categories, and this is suitable for classification. And for the reciprocal space, we use half of the data that we used, half of which we use for pre-training, and here we also use the labels, which is the Euler angles. We convert the Euler angles to quaternions and do regression. So we validate our approach on classification and regression. So our results show that physics-aligned SSL, that's what I'm going to refer to it. So that's the pre-training with physics-aligned augmentations. It improves classification accuracy over the standard augmentations. As you can see, we have a baseline model, the model trained from scratch that classifies, and it gets a score of 66.6%. And the pre-training with both augmentation methods outperform this baseline. But you can see that if you align the augmentations physically, you get a performance boost of 12% on masked autoencoder over the standard augmentation techniques. For Dino V2, the performance boost is about 10%, and it's around 4% for the redundancy reduction-based methods. The same applies to orientation regression. And here we can also see that pre-training with these augmentations outperforms the standard baseline, so the model trained from scratch, but also pre-training with physics-aligned augmentations outperforms the standard augmentation. So for Dino V2, we basically reduce the error by half, so from 10% geodesic error to 10 geodesic error to 5-degree geodesic error. And for VICREL, it's around 26% improvement, and for Sinclair, it's 15%. We also showed that this physics-aligned model is very robust to acquisition variability. So if there are changes in your image, for example, if you change the intensity of the image and then use the image to make predictions with the models, we show that it outperforms the standard SSL. So the intensity gain is basically, when you change the intensity gain, you basically simulate the change in the electron dose during imaging. And we can see that the physics-aligned model, so the solid lines, remain flat. It doesn't change the performance compared to the standard SSL when you change the dose, or when you simulate changing the dose. If you apply some Gaussian blur, which simulates the model, which simulates the detector point spread function, broadening, or the defocus effects, the trend still stays the same. The physics-aligned SSL models, the solid lines, they change comparatively lower compared to the standard SSL, the standard architectures. So basically, when you design augmentations that are aligned physically, the model is forced to learn the structures, so the basic, better representations, and not depend on acquisition artifacts. So if you change the artifacts, it remains very robust. So we showed that augmentations with which you pre-train your self-supervised learning approaches, they are the inductive bias, and you cannot just copy them from ImageNet. You have to design them to align well with the physics in your scientific domain. And this is very useful. As we showed, we gain around 10 to 12% improvement in classification accuracy. And also, we reduce the error in orientation regression. But even though we got performance boost on all the SSL pre-training approaches that are physically aligned, it's still very objective dependent. So for cross-view methods like DynaV2 and ImageJEPA, and also for the mask modeling approaches like mask autoencoder, the performance boost is very high. But for contrastive learning, even though there's still a performance boost, but the difference is not as much as to the previous pre-training approaches. So we applied pre-training with physics-aligned augmentations and validated to downstream tasks, classification and regression, but it would be important to see if the same performance persists when you apply the same approach to dense prediction tasks like semantic segmentation or tracking. So that will be the future work. So I would like to thank my colleagues at the Institute and also my group, Deep Learning for Electron Microscopy. This is a joint lab between our institute and the Forschungszentrum for Electron Microscopy at Forschungszentrum Jülich. We work on method development in deep learning and computer vision applied to electron microscopy. So if you are interested in our work and are willing to collaborate, please get in touch. And finally, I would like to thank you for your attention, thank the organizer for giving me the opportunity, and I would be happy to answer any questions you might have.
Thanks a lot. Are there any questions? I think we have time for one. Yes.
Yeah, thanks for the interesting talk. You talked of the gains through your augmentation method, but to me it stood out that the differences between the different architectures are actually much more significant and even vary between the two experiments that you did. So the masked autoencoder was very good at the second measurement, and the Simpler was very good at the first experiment. How do you explain these massive differences, and that especially for the best architectures, your augmentation doesn't seem to make a difference?
Yeah, thank you very much. That question was also what we had in mind when we designed our experiments and got the results. So basically, for the real space electron microscopy modality that we train, these are a scanning electron microscopy of different biological samples. But here, the difference between this domain and the natural domain is not as much as the difference between natural domain and the reciprocal space diffraction patterns. Because here, you have scanning electron microscopy images. The objects basically cover the majority of the image, the spatial location in the image, which is similar to natural images. So if you do some augmentations, like rotation, flipping, it doesn't change the physics as much as it does with the reciprocal space for this term. And that's why you can see the difference between those different families of SSL. Because, for example, in masked autoencoder, if you mask 75% of the image in order to pre-train your model, it doesn't matter much for the real space electron microscopy. But it matters a lot for the diffraction for the reciprocal space, because if your random seed somehow masks the central part of your diffraction pattern, you basically teach the model nothing. So that's why there's a discrepancy between the performances in different family of SSL models.
All right. Thanks a lot. Let's thank Bashir again.
Thank you.